All right. Yes. Hi, everyone. And I'm very happy to speak in this meeting. Very unfortunately, it's only by Zoom. I wish I could be there with everyone in person, but yeah, the UK bureaucracy won this time, so I wasn't able to come. But okay, so I will talk about a joint project with Kobi and Sergei, which luckily I had the pleasure of working with both of them recently on a joint project. And here you can see us all pictured working hard on this project in Oaxaca. So my talk is about some interactions of model theory and combinatorics. I think some of you might have seen some versions of this talk, so hopefully there will be something new in it, but also I apologize for part of it. So the running theme is the trichotomy principle in model theory, which says that in a sufficiently tame context, in a sufficiently tame class of first-order structures, which can be either certain strongly minimal theories, such as Zariski geometries, or strongly minimal theories definable in no-minimal structures, or something like this, or alternatively no-minimal structures. Every structure should, in some sense, fall into one of these classes. So it's either trivial in the sense of some associated matroid, or it is essentially a vector space, in which case such structures are called modular, or it interprets a field. And so asymptotic sizes of the intersections of definable sets with finite grids in similar model theoretically tame contexts turn out to reflect this trichotomy principle and detect the presence of algebraic structures such as groups and fields. So in this talk, I will try to present some connection between these combinatorial aspects and the more geometric aspects in the sense of the geometry of associated matroids or forking relation or something like this. And there are many instances of this principle which are well known in combinatorics. It is known that extremal configurations which somehow witness maximal bounds for various asymptotic counting questions, they turn to be robust and they turn to have some algebraic structure. And what I will discuss here is the inverse kind of theorems which tell you that this is the only way things can happen, that this algebraic structure is unavoidably occurs when we are considering some extremal configurations for certain class of problems. Okay, so historically, the very first instance of the kind of principle I'm talking about today is due to Erdős and Semiredi, the so-called sum product phenomenon. So it's a very, very easy principle. It says that there is an absolute constant, so that if I take any finite set of real numbers, and I can get the set of all sums from this set, or the set of all products from this set, and so we can see that the set is always of sums of products, at least one of them, is going to be significantly bigger than the set A itself. So namely, it's going to be of the size at least A to the power 1 plus this absolute positive constant. Okay, so the power strictly increases for at least one of them, either the sums or the products. Okay, and there are a lot of results on improving this bound. So it is expected that this holds with the, in fact, should hold with the power 4/3 plus epsilon. So not just 1 plus epsilon, but in fact, something like this. And in fact, conjecturally, it should get all the way to 2. So the power should grow almost as large as possible in this configuration. Okay, so now we have this two groups, the additive group and the multiplicative group. So what if we have a more complicated combination of the two? So this is a theorem of Elekes and Sergei, which says that take any polynomial in 2 variables with real coefficients of some fixed degree, okay? Then we still have the same expansion phenomenon. So namely, if I have 2 finite sets of real numbers of size n, and I look at the image of the direct product of these sets, So this simply consists of all numbers of the form f of AB. So where the pair AB is in the product of these two sets, A times B. And so this polynomial is going to be expanding in the sense, again, that this image has power strictly larger than 1. So the set gets significantly larger, unless f is of a very special form. So either it is essentially controlled by addition or by multiplication between the two variables. Yeah. So if there is any mixing of addition and multiplication in this essential mixing of addition and multiplication in this polynomial, then it is expanding. Okay, so again we get this sharp dichotomy, and an influential theorem of Elekes and Szabó provides a conceptual generalization of this fact and explains how algebraic groups appear in the picture, like why they explain this expansion phenomenon. So the original result proved by them in 2012 is concerned with ternary relations, okay? Which I will only, I mean, there are several related results, so I will present it in the simplest form for the purpose of this talk here. So the result is following. Assume we have an algebraic surface, R of x1, x2, x3, just in R cube for the purpose of this statement, and assume that the projection on any two coordinates is finite-to-one. Yeah. So if we fix two variables, there are infinitely many choices for the remaining variable. Then exactly one of the following two possibilities holds. Okay, so the first possibility is that there is power saving. So namely, there exists some positive number gamma, positive real number gamma, such that for any finite grid, n by n by n, so meaning we pick three sets, A1, A2, A3, or each of size n, and we look at the direct product of the sets, and we look at the intersection of our surface with this n by n grid, and we get that the cardinality of this is strictly below the maximal possible. So it's bounded by n to the power 2 minus some positive gamma. So the maximal possible number of intersections of such a surface with a grid would be n square, up to a constant, yeah, it would be n square, because two coordinates can vary independently, but the remaining coordinate, once we fix some two coordinates, we only have finitely many choices for the remaining one. So this gives n square, and so the first possibility of the dichotomy that there is power saving, so it's strictly below the maximal possible number, the maximal possible size of the intersection, or our relation R is closely connected to a group in the sense, well, in the local sense here, because we are working over the reals. So the second possibility is that there exist open sets, U1, U2, U3, okay, neighborhoods of identity, and there exists V, a neighborhood of identity, and we have analytic bijections, Pi, from UI to V, with analytic inverses, such that our relation R of x1, x2, x3, when we restrict to these neighborhoods, is essentially the addition, well, essentially the graph of the addition. So it's given by this pi1 of x1 plus pi2 of x2 plus pi3 of x3 is equal to 0. So we have that a relation is just, our relation R is given by this, by the graph of addition for all triples restricting to this neighborhood. Okay, so either locally our relation is controlled by the additive group, or we have power saving. And this is indeed the generalization of the previous result about expansion of polynomials, because we can consider R of x1, x2, x3 to be given by, let's say, x3 is equal to f of x1, x2 for some bivariate polynomial f, okay? And power saving here corresponds to the expansion, power saving of the graph corresponds to the expansion for the polynomial. So this is indeed a generalization of the previous result. Okay, the statement okay. Any questions at this point? If not, okay, I'll continue. So this result and its variance have become a quite recent area of research recently. So here I have a summary of some of the results towards generalizing the Elekes-Szabó theorem. So let me just highlight a few of them. So first of all, we want to consider relations of arbitrary arity, R. And so we have an algebraic surface of this form now. And we also want to work, we don't want to restrict to the assumption that each coordinate is one-dimensional. So now each coordinate is allowed to have arbitrary dimension, M, okay? And we are still, for the sake of this talk, we still assume that we have a finite-to-one projection onto any r-1 coordinates. So if we fix r-1 coordinates, there are only finitely many possibilities for the remaining coordinate. Okay. So in this setting, first of all, already Elekes and Szabó themselves proved the ternary case r equals 3 with M arbitrary, so arbitrary dimension of the coordinates over the complex numbers, where once one goes up to the higher dimension, one has to restrict to grids in general positions, so-called general position. So grids where only bounded number of points are cut out by varieties of smaller dimension. Okay, and in this case, they establish correspondence with complex algebraic group of dimension m, so same dimension of the coordinate. Okay, in this special case that I stated, we have correspondence with the additive group, so one-dimensional group. So here we have m-dimensional group. Then there was a sequence of generalizations. For example, Rush, Sharer, and Dezhov generalized it to four-dimensional, to relations of arity 4, but each coordinate of dimension 1. Then the Elekes-Szabó problem was generalized to arbitrary arity over the complex numbers still. Then influential generalization by Khrushchevsky treated this problem as an application of model theoretic modularity. So the connection with modularity was pointed out, and also the role of pseudo-finite dimension and counting played in this situation. Now, a general result by Bayes and Brouillard from 2018. It's crazy already, 4 years past or 5. It feels like it was yesterday. So established this over the complex numbers, for algebraic varieties over the complex numbers, for arbitrary arity and dimension of the coordinates, and also demonstrates that the rising algebraic groups are actually abelian, even though their methods are essentially infinitary, so don't provide bounds on the power-saving exponent gamma. So then there was a number of related works, some prior and some more recently or in progress. So in particular, this problem was considered over, or analogs of this problem were considered over finite fields, large finite fields, or pseudo-finite fields equivalently, for several polynomials at a time, expansion for several polynomials at a time. Or, for example, some recent work in progress tries to capture nilpotent groups as opposed to algebraic groups, which would be probably the more general situation. But okay, I won't focus on this. So I want to present joint work with Kobi and Sergei, where we consider the situation with arbitrary arity and dimension. But our generalization goes in the direction of also working with the context of definable sets in a sufficiently model theoretically tame structure. So, for example, a minimal structure or a stable structure with a distal expansion. Okay. So a special case. Let me state a special case of our result when the dimension of the coordinates is 1. Okay. So the situation is basically the same. Assume we have that R, so the arity of our relation is at least 3. Assume that M is a no-minimal expansion of the reals, of the field of reals, and assume that we have a relation of arity R, but each coordinate is one-dimensional in this statement for simplicity. Okay, so we have a definable relation R, so that the projection to any R-1 coordinates is finite-to-one. So the same situation as above, but now we have a definable relation in a no-minimal structure. Then the conclusion is as follows. So we have two possibilities for what might happen. Either we have power saving, in the sense that if I take any finite sets AI, each of size n, so I fix an n by n by n by n grid with R sets, a product of R sets of size n, and we look at the size of the intersection of R with such a grid, it's going to be strictly bounded away from the maximal possible number. So the maximal possible size of the intersection will be n to the power R-1, right? Because R-1 coordinates can vary freely, but the last one is determined once we fix the any R-1. But here, again, we get that it's strictly below maximum. So because we have this power saving, minus gamma, some positive exponent. And in fact, we have explicit bounds for gamma. We can either take gamma to be 1/3, or when R is at least 4, or 1/6 when R is 3. Okay, so explicit bound on power saving, or again, we're in close connection to the additive group. So there exist open sets UI and V, open set containing 0, and we have homeomorphisms from UI to V, such that restricting to this open neighborhoods, our relation is just the graph of the addition, an R-fold graph of the addition. Okay, so it's a natural generalization of the ternary case. All right. Okay, so now let me say how this modifies in the general case. So assume again, M is a no-minimal expansion of the reals. We have a relation of arity R, definable, but this time each coordinate xi is allowed to have any dimension we want, M. Okay, so now each coordinates of arbitrary dimension. Then one of the following holds, and I'm no longer claiming that these are mutually exclusive possibilities necessarily. So in the first case, we have power saving, but we have to restrict to grids in general position. Okay, so power saving is exactly as before, even though the exponents get a bit worse. So the power saving exponent gets a bit worse here. And this should be R. I apologize. This is R. Okay. So we have power saving, but on grids in general position. So what do I mean by grid in general position? Well, by this I mean that if I have, for example, a 3 by 3 by 3 grid of size n, general position means that there is some absolute bound, so that if I look at one coordinate, for example, at the first coordinate, if I intersect it with any variety of dimensions smaller than m, smaller than the dimension of xi, I only cut out a bounded number of points from such a grid. So somehow we want to look at sufficiently generic grids. Okay, this is the first possibility. And the second possibility is that, again, that our relation is essentially multiplication in, or even addition, let's say, in an abelian Lie group of dimension m. Okay, so there exists definable, relatively open sets UI in xi, an abelian Lie group G plus of dimension m, so it lives on one of the coordinates, let's say, of the relation, and an open neighborhood V, and definable homeomorphisms, excuse me, pi, so that again, restricting to the product of these neighborhoods, our relation is just the graph of addition in G. Yeah, so here, this is addition in G. Okay, so this is an appropriate generalization of the previous cases that I discussed. Okay, so it's a general result for minimal structures. Either you have small intersections with grids, or you essentially the graph of multiplication in a group, an R-fold graph of multiplication in a group. And I apologize, I think I have S again everywhere instead of R. So this should be all R instead of S. So R is the arity of the relation. All right, so this is a statement of the theorem. So I want to discuss the ingredients that go into a proof of this result. And well, and a couple of remarks also, I guess. So before discussing some ideas that go into the proof, a couple of remarks. So if M is minimal, but not elementarily equivalent to an expansion of the field of reals, the actual reals, we only get correspondence with a type definable group. Okay, and then over reals we can boost it to correspondence with the Lie group. Now, one ingredient is a semi-Trotter style bound in minimal structures, or even more generally in distal structures. So I'll say a couple of words about this. And the second ingredient is a higher arity generalization of the abelian group configuration theorem of Zilber and Hrushevsky on recognizing group from a generic chunk, along with a purely combinatorial version. In fact, in the minimal case, we used the purely combinatorial version, which can be viewed as a kind of coordinatization result, but like a purely combinatorial coordinatization result for the associated locally modular geometry. So let me say a couple of words about these ingredients. First, recognizing groups. So assume that now forget model theory for a second. So this is a purely, it's a completely general result. So assume G is an abelian group. Assume G is an abelian group. And we consider a relation R of arity little r, okay, given by the R-fold graph of addition in this group. So x1 plus etc. plus xr is equal to 0. Okay. Then it's easy to see that R satisfies the following two natural properties for any permutation of the variables of R, moreover. Okay. So the first property that if I fix R minus 1 coordinates, there's a unique choice for the remaining coordinate. Okay, so this is just a cancellation in a group. And also that if I fix any x1, x2, then for any two choices of the remaining coordinates, so y3 through yr and y3 prime through yr prime, if the relation holds between x and y and y prime, excuse me, then it also holds for any other x1 prime, x2 prime. So again, this is obvious for the graph of addition. Yeah, just because once you fix the other coordinates, you can calculate the sum of the remaining two. Okay, and so we show a converse that these two properties, P1 and P2, characterize when your relation is in correspondence with the group. So these two very simple properties. So namely, assume that R is at least 4, and we're given sets x1 through xr, and we're given a relation, array relation between the sets. So here, no definability assumptions, yeah, just sets, abstract sets. So that this relation satisfies P1 and P2, these properties for any permutation of its variables. Then there exists an abelian group, G, and bijections between each of the sets xi and then and this group, such that we have the same situation. The relation captures precisely the R-fold graph of addition in this group up to applying these bijections pi I. Okay, so we have a converse result, And moreover, this is a definable recovery of the group. So if R is definable in some structure, in some sufficiently saturated structure, M, and each of the sets Xi is type definable, then the group G is also type definable in M. And the maps, these bijections πi are relatively definable in M. Okay, so this result holds in the definable category, in fact. This is the first remark. And another remark is that this can be viewed somehow as a characterization of those latent hypercubes which come from abelian groups. Which is a higher order generalization of latent squares. Okay. All right. So we have this. This is a purely combinatorial version of this group reconstruction. And we also have, when I'm working in a stable theory, the stable version of this theorem, we have to relax these bijections with the group to generic correspondence of the type definable group. So let me state it quickly. So assume we will say that a tuple A1 through AR is an argon if any R-1 of its elements are independent in the sense of forking in a stable theory, and any element is in the algebraic closure of the other ones. Yeah, so if we fix any R-1, the remaining one is in the algebraic closure of them. Okay, and we will say that an argon is abelian if for any permutation of the elements we have a property which corresponds to modularity. So somehow this is local modularity, just restricting to the elements of this tuple. Yeah. So any two are independent from the remaining ones over the intersection of the algebraic closures of the left-hand side and of the right-hand side. So this is a familiar property of forking modularity, but now we are only requiring it restricting to this tuple. Okay. And if we are given a type definable abelian group G, well, in any group, if we take R-1 independent generics and add one more element, which is the product of this R-1 independent generics, then we will get an argon. And if the group is abelian, this is going to be an abelian argon associated to our group G. Okay, so in every group, if you pick a generic configuration like this, in any abelian group, you get an abelian argon. And conversely, given an argon, we can recover a group associated to it. So this result was also independently, well, even earlier was proved by Khrushchevsky, actually. So assume, again, R is greater or equal than 4, and we have an abelian argon, A1 through AR. Then there is a type definable, and here we have to work with the imaginaries. So working in MEQ, there is a type definable connected abelian group, G, and an abelian argon, G1 through GR, associated to G. So just like I said here, yeah, an independent product of generics plus one more element, such that after a base change, each element GI is interalgebraic with AI. Okay, so we get this interalgebraic of correspondence question, sorry.
Yeah, what is M here in this theorem?
What is M? M is some saturated structure. So
stable?
We work in some, yes, stable. So T is stable, sorry. Yeah. Yeah, so we work in a stable structure. So we have an argon, an abelian argon in a stable structure. And yeah. And in the end, we can recover a group like this. So note that, like I said, in the stable case, we only get generic correspondence, or let's say it's up to interalgebraicity. So we don't get a bijection, we only get somehow finite to finite correspondence between our configuration and the group. Okay. So so this is the stable version of the result on recovering the group. And let me mention the second ingredient. Okay, unless there's any questions about this one. Okay, let me mention the second ingredient, distality. So here's the definition. One of the possible definitions of distality. I mean, it's not the original definition of Simon, but it's an equivalent. We proved that it is equivalent. And this is a more combinatorially explicit and accessible version. So we say that a structure M is distal if and only if for every definable family, phi of xb, for b a varying parameter, of subsets of mx, the sort of M corresponding to x, we have another definable family, theta of xc, okay, such that for every element A and every finite set B, okay, so I have A, I have B, we can find some C, a parameter, a tuple of parameters in this set, okay, such that A satisfies theta of xc and theta of xc isolates the phi type of A over B. So note that the size of B is not bounded. B is an arbitrary finite set. So we have a bunch of conditions whether phi holds with A or not for different elements of the set B, arbitrary large. Yeah. So for example, I have like it holds with this one, but maybe not with this one. So maybe this is B1, this is B2, this is phi of x B1, this is phi of x B2, etc. So what theta gives us is a set small enough around A so that it implies the phi type with respect to all elements of B simultaneously. Yeah. So a single formula isolates the phi type over an arbitrary large finite set B. Yeah, and note that this theta only depends on phi, not on the choice of B. Otherwise, of course, it would be trivial. Okay, so this is distality. Let me mention some examples and non-examples of distal structures. So first of all, any distal structure is in NIP and unstable. However, an important point about distal structures is that distality is not preserved under reducts. Yeah, like if I go to a reduct, I might lose this formula theta, which provided the isolating definition for phi types. So it's not closed under reducts. Some examples of distal structures are weakly or minimal structures, various valued fields of characteristic 0, such as QP, RCVF, trans-series. Okay, so we have a bunch of characteristic 0 valued fields. And like I said, it's not closed under reducts. So it's actually an interesting question to understand which distal structure, which NIP structures have distal expansions, or which stable structures even have distal expansions, which is exactly the context in which is needed for the Elekes-Szabó theorem, for general Elekes-Szabó theorem. So let me just mention a couple of stable structures with distal expansions: algebraically closed fields of characteristic 0, differentially closed fields of characteristic 0, possibly with multiple commuting derivations, compact complex manifolds, arbitrary abelian groups, and Khrushchevsky constructions. So here I put a star because what we know, and this is some unpublished result with Pierre Simon, we know that the uncollapsed ones are, the uncollapsed Khrushchevsky constructions actually have a distal expansion, but once you collapse, it's actually, we don't know if it has the actual distal expansion or not, but it satisfies all combinatorial consequences. Somehow it's locally distal, which is maybe a more robust notion. And now we have several examples of stable structures without distal expansions. So for a while, we only knew one, algebraically closed fields of characteristic P. More recently, it was observed by Jiang, Nesetrel, Asonia de Mendes, and Sieberts that maybe the reason for the failure, well, definitely one reason for the failure of having a distal expansion comes from appropriate expander graphs. So, for example, if you have a sequence of Ramanujan graphs of growing degree and expansion, and you take a disjoint union, then it has no distal expansions. And very recently, also, there's an interesting example in continuous logic. Namely, if I take any Banach space, it doesn't admit a distal expansion. So this follows from a result of Hansen. And let me also mention that gestalting continuous logic is developed by my student, Aaron Anderson. So it's a new kind of example, it seems, that we have in continuous logic. We don't know if the reason is the same or not as for the failure to admit a distal expansion in discrete structures. Okay. An open problem is if non-abelian free groups have distal expansion. So
Can I ask a question? Sorry.
Yes, please go ahead.
Do you have an example where you said there was also construction, but we just start? Do you have an actual example where the combinatorial properties do hold, but there's no distal expansion? Yeah,
that's open. We don't know. Krzyzewski construction may be an example potentially, but we don't know if it has a distal expansion or not. Yeah. But yeah, it would be interesting. The same question is open for Banach spaces, because what Hansen shows is that any expansion of a Banach space has an infinite totally indiscernible set, which rules out distality. But actually, it's not clear if you still have like an appropriate continuous version of the strong Erdős-Heinel property or not, for example. Yeah, so that's open. We don't have any example where we know for sure that the failure comes from combinatorics. Yeah. Sorry, if we know that there's any example where the failure doesn't come from the failure of combinatorics already. Okay. Yeah. Okay. And so distality. What's the use of distality? How does distality enter the picture? Well, turns out that one can establish improved incidence bounds, also called generalized incidence bounds, in structures with distal expansions. So, namely, the following is just a classical result from extremal combinatorics. Assume I have an R hypergraph, so relation of arity R, with each part of size n, okay, and assume that it doesn't contain the complete hypergraph with each part of size k. So you should think about this as k being fixed. Now, for example, we have k to 2, so it means I have 2 points in each part, and I have all possible edges between them. Yeah. Okay, and k2 to 2, for example, would be like this. So I have all possible triples. Okay, so once you rule out something like this, then there's a non-trivial trade-off on the possible number of edges in a hypergraph like this. Okay, but so the maximum would be n to the r if I have all possible r tuples in my relation between parts of size n. We would have the maximal number n to the r. But once you rule out a small complete hypergraph, there is some non-trivial bound for the number of edges in the whole graph. Okay. So the exponent is slightly better than maximal possible, and this result is essentially optimal in general. However, it turns out that if your hypergraph is definable in a distal structure, or then we get a better bound. We get a non-trivially better bound. So, namely, and here this result was Galvin and Sergei generalizing the semi-algebraic case that was known in combinatorics. And all of this, of course, generalizes the celebrated semi-Regget-Rotor theorem on the number of incidences between points and lines. Okay, so what we say is that, let me just state it for binary here. So assume I have a definable binary relation in a distal structure, then which emits complete bipartite graph on k vertices on each part of size k. Then the number of edges is going to be, so again, we only care about the exponents, yeah, ignore all the constants. So the exponent is going to be t minus epsilon, where t is the exponent given by the basic bound on the previous slide, which was known to be optimal for general graphs. Yeah. So we get some non-trivial improvement over general hypergraphs, or graphs even, in the situation where the graph is definable in distal structure. And this epsilon, this improvement, is exactly what translates into the power saving in the Elekes-Szabó theorem. Yeah, so that's exactly what. So it's important to have this non-trivial improvement, because without this, we wouldn't be able to get power saving in the Elekes-Szabó theorem in the case when there's no group. Okay. So this is okay. Yeah. So when should I stop? Sorry, is it time to stop, or do I have more time?
10 more minutes.
10 more minutes? Oh, okay, great. Okay. So we have this non-trivial improvement, right? And this is the second ingredient. So the power saving here translates into power saving in the non-group case of the Elekes-Szabó theorem, and otherwise we are able to find a configuration like the n-gon, for example, the abelian n-gon, using which we can recover a group and then can establish this coordinatization result for the relation by this group. So these are the two main ingredients, but also connecting them is not entirely trivial. Yeah. But okay, so this is somehow the two main ingredients that go into the proof of that result. So this is about recognizing groups. And I also want to say a few things about recognizing fields from sizes of intersections with grids for a definable relation. Okay, so consider the following example. Consider we have just the semi-algebraic point-line incidence relation, the one I mentioned from the semi-Ready-Trotler theorem. So it is K2 free. Why? Because if I fix any 2 points, they determine a line. Yeah. So I cannot have 2 different points and 2 different lines with incidences between all incidences between them. Those 2 points determine a line. So it's K2 free. It's clearly definable, even semi-algebraic, and it is known that the optimal lower bound is of this form, n to the power of 4/3. Okay, so in particular, it's not linear. So it's known. The lower bound is known in this case. Note that to define this relation, we use both addition and multiplication. So we are using the field structure. And turns out that this is not a coincidence. So it turns out that any non-trivial lower bound on such on the number of edges in a K2 free graph allows to recover a field. Okay, at least in the minimal situation. So this is going to be a result about the minimal structures. So namely, so this is a result joined with Abdul Basit, Sergei, Terence Tao, and Chomin Tran. So assume we have M, a no-minimal structure, and assume we have a relation of arity R, okay, definable relation, which is KKK free. Okay, but assume that if we look at the size of the intersection of this relation with a grid, then asymptotically it's not of the form n to the power r minus 1. Yeah. So for example, if the relation is binary, assume that asymptotically the number of edges is not linear. Yeah, that's assuming that it's not super linear. Linear would be the best possible bound under any circumstances. So assume that it's not. Then a real closed field is definable from this relation. Yeah. So this relation already allows us to recover addition and multiplication. So this, in some sense, is a converse to this discussion. Okay. So this is our result in recognizing fields. Let me say briefly a couple of things about the ingredients again. So one ingredient is, of course, the trichotomy theorem for minimal structures by Peterzil and Starchenko. And the other ingredient is an almost optimal bound on the number of edges in KKK free graphs, which are definable in locally modular or minimal expansions of groups. Okay, so for example, for semi-linear hypergraphs. Let me briefly recall local modularity in the minimal case, in the minimal setting. So let's write A is independent from B over C to denote independence, to denote algebraic independence in a minimal structure. Yeah, so to denote that the dimension of A over BC is the same as the dimension of the tuple A over C. And a minimal structure is called weakly locally modular if it is like locally modular, but up to a base change, but maybe making a base change. Yeah. So namely that for any two small subsets A and B, there exists some small C independent from AB over the empty set, such that we have the modular, again, the modular condition. So A is independent from B over the intersection of ACL AC and ACL BC. So the intuition here is that, of course, local modularity should reflect that the algebraic closure operator behaves like the linear span in a vector space as opposed to the algebraic closure in a field. Yeah. And in particular, so this is the notion of modularity in minimal structures, which characterizes no normal interpretable families of plane curves of dimension higher than 1. Okay, so this is equivalent to that one in the minimal structures. I think this is a result of Bernstein-Vassiliev, that this is the correct definition for this in terms of like a independence relation. Okay, and so the bound is as follows. So the bound on the number of edges is as follows. Assume we have a minimal locally modular expansion of a group M and a definable relation Q of arity at least 2. Then for any epsilon and any finite grid, n by n by n by n grid, if our graph, so we look at the relation intersected with this grid, if this is KKK free, so if this doesn't contain a complete graph, a complete hypergraph, excuse me, on K vertices, then we get a bound which is all the way down. So the maximal again would be n minus r, remember, but now we get the trade-off of whole exponent, so n r minus 1, but plus epsilon. So up to arbitrary small epsilon, we go down the whole exponent. And oh yeah, and moreover, the whole relation Q itself is KKK free, as opposed to just its restrictions to the restriction to the grid. Then we get the whole exponent, so we don't need epsilons in this more restrictive case. Okay. So this is the bound on the number of edges. And the other ingredient is the trichotomy, or minimal trichotomy of Peterzil Starchenko. So if M is not locally modular, then there exists a real closed field definable in M. Okay, there's also, and also I mentioned here a more explicit earlier result, specifically for semi-algebraic sets. So the point, okay, so combining these two results, now the trichotomy and this optimal bound, we show that we can conclude. So we can deduce that non-triviality of the Zarankevich bound implies that the field is definable. Okay. The result is quite infinitary, of course, especially in the part of the proof of the trichotomy. So it would be quite interesting to understand if we can establish a more explicit correspondence between the relation with many edges and the, let's say, the point incidence relation in this field that we recover. Okay, but that might be very difficult. This seems to be connected to some long-standing open problems and combinatorics. Okay, so I think I will stop. Maybe let me just mention one thing, which is a very recent development. So this upper bound for semilinear relations that we establish here allows to obtain a new incidence bound between points and boxes with axis parallel sides. So ignore the first part, please. Let's just look at this statement. It says that if I have n boxes where by box I mean a rectangle, solid rectangle, with axis parallel sides, and I have n points, and assume that the incidence graph between these two sets is free, then we get that the number of incidences is almost linear. So we have this epsilon in the theorem here, which I didn't elaborate on. In fact, the actual bound we get is n times some power of the logarithm. Okay. And we have demonstrated in that paper already that you need it, so that logarithmic factor was necessary, at least for on the plane, but the higher dimensional case was open. And a new preprint just came out by Harpelet and Chan, which is actually very interesting. So first of all, they improve our upper bound to the optimal one. Sorry, they improve the upper bound to this one. And moreover, it turns out that its optimality is actually shown by an existing result. So we asked this question, but turns out that this question already has been answered 30 years ago by Chazelle. Well, it's not obvious. I mean, it's like very different language. So Chazelle, this result of Chazelle from the 1990, on data structures. Oh, and these two people, by the way, they're computer scientists. But this result of Chazelle actually shows optimality of this bound for all D. Okay, so it's a quite curious fact. We had this new question, but turns out it has been answered a long time ago in a different language. Okay, so yeah, but I think I'll stop here. So thank you very much. Thank you.